Hi there, Science 9 students. So today we're going to look at Lesson 12 from your notes package. Topic of that is polyatomic ions. So you'll see that right here, there, Lesson 12. And I'm going to define for you what a polyatomic ion is, and look at some, and look at how to name them, how to give their formulas. So we'll get started. I'll just focus on the notes that I've written up here. They're similar to the notes you already have, but you might want to take down any extra information that I thought to put up here that wasn't there originally. So a polyatomic ion is an ion that is made up of more than one atom. So far I've dealt with ions like, say, the chloride ion, or the potassium ion, or the sodium ion. Ions that are made out of a single atom with an electric charge. Your metals, their electric charge is going to be positive because when they react to make an ionic compound, they give away electrons. Your nonmetals, almost all the time, usually I should say, when they're involved in a chemical reaction, they are accepting electrons, which means they get a negative electric charge. So you've looked at that. What you haven't looked at so much is situations where you've got ions that are made out of more than one atom. So, in other words, you have a situation where an atom might be bonded together with other atoms, and as an entire package, overall, that's got a charge, either more electrons than protons, so negative charge, or more protons than electrons, means that's got a positive charge. Things to know about these polyatomic ions: first of all, you're going to see a lot of examples. This is going to come up a lot when you're taking chemistry. So nitrate, sulfate, hydroxide are some examples. The rules for naming and formulas are pretty much the same as you get for naming binary ionic compounds. Pretty much the same, but I'd like to go into maybe some common mistakes today, and I'd also like to show you a bit about the structure, right? It's one thing for me to tell you that they're made up of more than one atom, but a lot of people like a bit more of a visual. So there's a whole bunch of them. I've written up just a sample of them in the table. I chose those ones for your notes table that you're going to see pretty often in high school chemistry. You just have to recognize there's probably hundreds more polyatomic ions that you are unlikely to see in high school chemistry. So here are four of them. Excuse the writing if it's not perfect. The nitrate ion, you could pause the video whenever you want. The hydroxide ion right here in the middle, hydroxide. Now in the middle is the sulfate ion. And lastly, the ammonium ion. I'd like you to look there, right here. It shows you it's got a positive electrical charge. All the others had a negative one. And here, the cyanide ion. Things to notice about those. Many of them have got more than two atoms in them. When that's the case, what you're going to see is you have one atom that's kind of in the middle, and your other atoms are joined to it. That's the usual rule. It can be violated sometimes, but it's the usual rule, is that you have that situation of an atom in the middle, another atom's bonded to it. Very often, that atom in the middle is going to be something like nitrogen, phosphorus, sulfur, and very often, in fact, even more often, I should say, especially for high school chemistry courses, the atoms surrounding it are going to be oxygen. Just a really common pattern, though there are exceptions to it. That's one thing I wanted you to see. So, for example, the nitrate ion, the first one I showed you, has got a nitrogen atom in the middle, and it's bonded to 3 oxygen atoms. But there's no such thing as a chemical that's just nitrate. No. Nitrate is an ion, so it only becomes a chemical when it's bonded to something. It's got a positive charge, because the whole packet that is a nitrate ion has a negative charge. You could go back to that video paused right there. Well, maybe have a look right here. You'll see it's got a little minus there, and the minus means a negative charge. Also to know, and this is maybe a little bit more relevant to like more advanced chemistry courses, but I would like you to notice the lines that I have between the atoms. This is more Chem 11, but I'd like you to understand it because I wrote it up there. Those are chemical bonds. So we had a nitrogen atom, and then it had what looked like an equal sign to another oxygen, to an oxygen, and another oxygen. And then it had actually a single bond, one chemical bond to a third oxygen. Those are chemical bonds. When you have one line between your two atoms, that's a single bond. When there's two lines, it's a double bond. And occasionally, just now and then, you're going to see three lines, like that. That's called a triple bond. It's a very powerful bond that can exist between some atoms. Not super common, but I'm going to give you an example. So those are some example polyatomic ions. You've got some that you're really going to see quite a lot. One of them, and you can go back to this if you want, is this one right here, OH, with a minus. Those of you taking more advanced chemistry courses are going to see a lot of chemicals that have OH in them, but there's a really important kind of distinction to make here. Sometimes there's just like a big molecule and it's got an oxygen and a hydrogen sticking off from it somewhere. That's called an alcohol. But you don't have to worry about alcohols till grade 11. You do have to worry about hydroxide. Hydroxide is an ion, so it's, again, a charged particle. It's got two atoms, so more than one, which means it's a polyatomic ion. And hydroxide is really important because when it combines with a metal, you get something called a base. That's a bit more like a science 10 level. But you're gonna see hydroxide in the future because hydroxide ions involved in a lot of chemical reactions. That's why I put it up there. So others are going to include sulfate. I've shown you some sulfates. We use them in some of our labs. Ammonium, which I put up there for a reason I'll show you in a second. Then just because I thought I'd put up cyanide, I put up cyanide because that's one of those examples with a triple bond. It's got a carbon, and then it's got a triple bond, a very tight bond to a nitrogen atom, and then you're going to notice those square brackets because they're always there, those square brackets. The square brackets means this is what's true of everything inside here. What's true about it is the charge. So sometimes you're going to have a positive charge, sometimes a negative charge. Again, usually it's a negative electric charge, but there's exceptions. That's why I put the ammonium ion up there. Because that's got a positive electrical charge. Most of them have a negative charge. I'd like you to notice something else about one of the ions I drew up here. And that is this sulfate ion right here. I didn't just put minus there. I'm not just saying, hey, it's got a negative charge. I'm saying specifically it's got a 2 minus charge. You looked at examples of this already, like the oxide ion, that is oxygen, as an ion, has got 2 more electrons and protons, so it's got a negative 2 charge. The sulfate, that entire packet, that polyatomic ion, also has an overall negative 2 charge. In other words, that sulfur with 4 oxygen atoms around it has 2 more electrons than it does protons. What does that look like in some chemicals? Well, here's an example. This is copper sulfate. Specifically copper 2 sulfate. By the way, here's copper nitrate. Looks pretty similar. One thing that would have come through in your lab, the Flames lab, is that when it comes to color, it's usually the metal ion that decides it. So in fact, if we look at, say, copper carbonate, again, it's blue. All these copper salts end up being blue. Salts of the iron ion are a rusty kind of a rusty color. Again, there are some exceptions to that. I thought I'd show you some of this today as well if you're interested. Maybe more towards the end of the video. What I want to do for all of you just now is I'd like to show you how to name these compounds and how to get the formulas for them. The problems I've chosen are from the notes package, so you can fill in the answers to the notes package as we go. And the questions I put on the worksheet that I'm going to post pretty soon are going to be similar. It's all the same content. Just a heads up, some of what I put up here, some of these examples, are going to be for multivalent metals. These are the most complicated chemical names and formulas that you're going to see in Science 9. If you've got a metal that's multivalent combined with a polyatomic ion, that name gets a bit complicated and there's a few pitfall mistakes I'd like you to do your best to avoid. So let's go through a few. So I'm looking here at lesson 13, lesson 12, the second page of it. And I have a little table a bit more than halfway down the page that's got the names of some of these, the formulas for some of these compounds. All these instructions are in your notes anyways, but it's my job to give you a little extra help. The first compound that we see is KNO3. Now, let's actually run through this using the instructions I gave. 1. The chemical name starts with the element on the left. This is a metal. Even though it is an ion with a positive charge, you still give it the element name. Get the element name from the metal, from the periodic table. Find the symbol and give the name. Well, when you go to the periodic table, you'll find that's potassium. We also want to look to see, is this multivalent? If it is, then you're going to have to use one of those Roman numerals. In the periodic table, next to K, it just has plus, nothing else. No like plus 2, plus 3, it's just plus. That means it's only got one possible charge, positive one charge, and so you don't need the Roman numerals. So we can move on from that. Now, it does say that sometimes if the polyatomic ion comes first in the name, then it means it's a positive charge. My exception then is going to be the ammonium ion, and I'll get into one of those as well. If the metal is not multivalent, follow step 2 to figure out how to find the right numeral. If it is, I mean. The second part of the name is the polyatomic ion. I'm on step 3 now. You get this straight from the table of ion names. You may see that the ion symbol is inside brackets, but for giving a name, you don't need to include the brackets. So NO3 is the nitrate ion. And that's really it. I just read from right to left to get that name. I identified the metal, I identified the polyatomic ion, and figuring out as well that the metal is not multivalent gives us a nice simple name. This is potassium nitrate. Let's look at another one. I'm going to go to the thing that says, no, I won't. I'm going to just go to the second one, CaNO3 too. Some of you already know that the Ca element is calcium, so we can throw that in already. And I just told you that NO3 is nitrate. This is calcium nitrate. Pretty straightforward, that, I think. Now, let's go forward, though, and choose a couple more problems within that same table. FeSO4 and Fe2SO43. I've chosen those for a reason. We're going to review those, and maybe we'll review a couple more from this table. But I want to go through those because these are the slightly more difficult ones. All right, let's start with the easy part. Periodic table will tell you, if you don't already know, that Fe is iron. In fact, we can put iron for both of these because they both say Fe. But when you look in the periodic table, you're going to notice that it's multivalent. You kind of already have a clue that it is, because we've got two different salts of iron that have different formulas. So it pretty much tells you already that it's multivalent. So that's something you're going to have to worry about. You need to find the charge. All right. You do this, find it using the exact same rules I already showed you. Well, let's see. That SO4, well, we got to find what that is, don't we? SO4, that table of polyatomic ions on the first page of lesson 12 is called sulfate. Now, I'm writing a bit of space between the iron and the sulfate. I'm going to write it over here as well for this other one. I'm leaving a little bit of space because we're going to need a Roman numeral. Now, I'm going to tell you, first of all, a mistake that some people might make. They might be like, oh, I guess there's just one iron here, so we're going to call this iron 1 sulfate. That would be a mistake. It would be a mistake in the same way if you say, hey, that subscript there for the iron, and this one here is a 2. I guess this is iron 2 sulfate. No, it's not. That would be a mistake. You need to find the subscript, excuse me, you need to find the Roman numeral by finding the charge. How do you find the charge? You use the charge on the polyatomic ion. Let's start with this one right here, SO4. All right, so SO4, the table of values tells me that it's got a -2 charge. That's sulfate. It always has a -2 charge. That is balanced out by a charge on the iron. In the name for an ionic compound, the electric charges always have to balance. So that 2- has to be balanced by a 2+. And now we have enough information to make our formula. This is iron 2 sulfate. Done. That's the formula for FeSO4 that you see there in the table. Now the next one here, Fe2SO4 3. I haven't even left that space here. Done. So here, oh gosh, the first thing I'd like you to know is this. For that polyatomic ion, we use brackets. What do the brackets mean? The brackets just mean that if there's a subscript, I'll put it this way. You only need to use the brackets when there's going to be a subscript for that ion. So, in other words, if there's more than one sulfate, you need to use brackets. I'd like you to notice for FeSO4, I only had one sulfate, so I don't need any brackets. But here, this is saying, those brackets are telling us that there's 3 sulfates in that compound. How do I know? Because there's outside the brackets, there's that 3. That 3 means 3 sulfates. Just like the 2 for the iron means 2 irons. How do we use that information? Well, if we've got 3 sulfates, I'm going to draw them out here. SO4 2-. That's a lot of sulfates. And each one has a -2 charge. The total negative charge is there. Well, you got to add up those negative charges. Total negative charge is -6. So we're going to have to balance that with a +6 electric charge from the irons. All right. Well, there's 2 irons to do that. 6 divided by 2 is 3, as you all know. What is that? That is the ion charge on the iron. So you might remember now that if you want to do the Roman numeral thing, you need ///. 3 i's in a row gives you that ion charge that you need, and you put it after the iron. So this is iron 3 sulfate. So those are 2 different compounds. And I'll just say again, when it comes to Science 9, in my opinion, these are probably the most difficult chemical names to know. There and right there. Okay? Iron 2 sulfate and iron 3 sulfate. There's a couple more I'll go over just now. And you know, like if you get that from what I've told you, then just fast forward through the video. Don't worry about it. Let's go through, I don't know, third one, that really long one, NaCH3COO, and maybe NH4OH. These are also from that table. Let's figure out the names. Again, if you get it, just go forward. Do what you need to do. So we get a formula that is NaCH3COO. We have another formula that is NH4OH. All right. Well, for this one right here, that's actually not too bad. You probably know by now that Na is sodium. Let's put that down there right away. So all we need to do now is to be like, wow, that is a really long rest of the formula. But you've identified that the positive ion is sodium, so everything else is that negative ion. This is the stuff that gives salt and vinegar chips their kind of vinegary flavor without pouring a bunch of vinegar on them. It's called sodium acetate because the CH3COO is the acetate ion. But how about this one, NH4OH? Where's the metal? There's no metal. This is one of those examples where you have a polyatomic ion that's positive. For high school chemistry, most of your polyatomic ions are negative. Here's an exception. The NH4 is this thing right here, the ammonium, NH4 plus, a nitrogen with 4 hydrogen atoms around it with an overall +1 charge. Then we've got that OH minus. Oh, there it is, hydroxide. So in fact, this is just a matter of knowing your names of your ions. This stuff here is ammonium hydroxide. You know, I think there's one other I'd like to show you, I'm gonna actually show it to you literally, and I'm gonna show it to you on the board. Let me show it to you literally first. I'm gonna get a test tube. One of the most useful chemicals in high school chemistry is this stuff right here. Where is it? Here. Notice that color. It probably looks black through the camera. It's not actually black. They are richly deep violet crystals. This is also extremely soluble. I've actually shown this to you before, this chemical. The chemical is the chemical I showed you in the chameleon reaction. So let's have a look at what happens when you try to put some in water. Here is the amount that I'm putting in water. Yes, that is really a very small amount. This is far less than a gram. If I was to make a guess, I'd say it's 0.1 grams. Poured it in. You see it's already starting to dissolve. Let's get a white background to that. Notes to brick fine. This is often used in grade 8 chemistry as an example of diffusion. The crystals are of this compound, it's such soluble stuff that as the crystals sink to the bottom, they leave a purple trail behind them. By the time they're at the bottom, the crystals are almost gone. But there it is. Beautiful purple color. This is also a very reactive substance, and you can cause it to change its color and turn it to different chemicals when you put it in different kinds of chemical environments. That's more a subject for Chem 12, but I'm going to go through its formula right now. And then I'm going to go through its name. If you look on the chemical container, you're going to see this. You're going to see what it says is KMnO4. Here, you'd be excused for being like, wow, okay, how am I going to name that? Because if you go to the periodic table, you're going to see the K is a metal. It's potassium. I already told you that. But then you're going to also see that Mn is a metal too. It's in the metal part of the periodic table. It's called manganese. So you might be tempted to be like, okay, I guess I'm going to call that potassium manganese 4-oxide or tetraoxide or just oxide. There might be some confusion involved there. The deal is this. The MnO4 is its own thing. It's another polyatomic ion. It's one of these examples of a polyatomic ion that's got a metal in it, because there's some of them. So I'm going to go through the name of this one. Here, the first name is simple. K. It's potassium. And here, the MnO4 part, that's a polyatomic ion. That is called the permanganate ion. And there's a few other examples of this. They won't let you handle them until further in high school chemistry because a lot of them are actually quite toxic. Like the chromate ion, for example. Nasty stuff, useful for a lot of chemistry experiments. And they're polyatomic ions that have a metal in them. Again, though, you've got that case where there's lots of oxygens in them. It's a pretty common thing to see. And you've got the situation where if you were to look at that ion, if you had an impossibly powerful microscope, you would see a little manganese atom in the middle and 1, 2, 3, 4 oxygen atoms surrounding it. And the overall charge of that, some of you probably know that already, but some of you won't. The overall charge of it is -1. And how do we know that? Because there's no subscripts for the K, and the K is a +1, so the charge has to balance. So that means the permanganate must be -1. In fact, if you look in the table for lesson 12, the first page of lesson 12, you're going to, I think, see permanganate. Totally didn't put it there. No big deal. There are some even some exceptions to that. Sometimes you do name both metals, but I'm not going to go into that. I'm just going to tell you that there are some polyatomic ions that have got metals in them. What I'm going to go through next is are some of these examples right here for making the formula. Yep, good. Okay. So on the second example, now you got to work backwards. You're being given the name, and now we need a formula. And that's a bit harder. It's a bit harder because just having the formula, it's not a lot of information. Just having the name, it's not a lot of information because what it is lacking is it's lacking the subscripts. It doesn't tell you the subscripts. You have to figure out the subscripts, and that's what's more difficult about going from name to formula. I'll tell you one thing. You cannot get the subscripts from the Roman numerals. Say that again, because it's a super common mistake. Those Roman numerals are not the subscripts. I guess I should say you can get them from the subscripts, but the Roman numerals themselves aren't the subscripts. The computer charger's not working. Okay, good. Let's go through some examples. The first example that is given is calcium carbonate. All right, we're working the other way now. Well, what's the symbol for calcium? Periodic table will tell you it's Ca. How about carbonate? For that, you're not going to find these polyatomic ions in the periodic table. It's a very common mistake to look for them there. So you're going to find them in a table of polyatomic ions. And this one's not too hard because the calcium and the carbonate have got the same ion charge. Another really common mistake I see when people are dealing with carbonate, again, they're looking for those polyatomic ions in the periodic table and they see CO and they're like, oh, I guess that is cobalt. This often works when people are going from formula to name and they see that CO3 in there. They're like, oh, okay, periodic table, what's CO? That's cobalt. A very common mistake I've seen is someone being like, okay, Na2CO3, I guess that's sodium cobalt trioxide. No, it's not. The CO3 is a polyatomic ion with its own charge, and it's just called carbonate. You're not going to find these in the periodic table. You need a separate source for them. Calcium carbonate is CaCO3. Let's go through zinc chlorate, just because. All right, well, zinc is Zn. That's simple enough. The chlorate ion is a chlorine atom that's got more oxygens than it does. It's got 4 oxygens and 1 chlorine. Oh, I'm sorry, it's got 3 oxygens. ZnClO3. But I'm not done. That's not the correct formula. Why isn't it the correct formula? Because zinc has a +2 charge. Here, I'm going to throw these out here. Zn has got a 2+ charge. ClO3 has got a -1 charge. So ZnClO3 is wrong. It's not finished yet. Because we need 2 of these chlorates to balance the 1 zinc. So the full formula for this is ZnClO3, and we need brackets. Specifically, we need brackets around the polyatomic ion. And because we need 2 of them, we have those brackets around the ion and put a little number 2. And that means that we've got, for the formula, 1 zinc and 2 chlorates. The formula is now balanced. The positives balance the negatives because that's the rule you always have to follow. And it works here. So let's look at another one. Wrong page. Rubidium hydrogen carbonate. All right. Rubidium hydrogen carbonate. This one's a little bit tricky because you might ask yourself, all right, what's the, it's a 3-part name, right? Most of them are 2-part names. This is one of the 3-part name. You've got the carbonate ion, that's just CO3. The hydrogen carbonate ion is actually its own thing. It's H with a CO3. You've heard of this stuff, but you haven't heard of the name. Because another name for the hydrogen carbonate ion is bicarbonate. If you've made pancakes, you've worked with the bicarbonate ion. It's a hydrogen joined to a carbonate. Periodic table will tell you the rubidium's got a +1 charge. Your table of names for polyatomic ions not the periodic table, but the table of names, which is a separate thing, will tell you that hydrogen carbonate, that's your package, that's your polyatomic ion, has got a -1 charge. So the rest of the formula is not too hard because the positive one balances the negative one perfectly. So this is RbHCO3. Let's look at a couple more. I'm going to look at copper 2 chlorite and then a couple of manganese ones. And then I'll just show you something cool and then we're done. So, copper to chlorite, and then I'm going to two of them that involve manganese. Manganese 2-phosphate. And then I'm also going to do manganese 3-phosphate. Sorry, my writing's not super neat there, but you've already got all this written in your notes. All right, that is this table right here on the 3rd page of your notes. Copper 2 chlorite. All right. Let's find the formula for the chlorite ion. Because how do we know well, first of all, how do we know it's a polyatomic ion? Well, because it's not chloride. That might be a mistake some people would make. They might, be like, okay, I guess Mr. Coop misspelled chloride. No, I never misspell things. Or if you let's see if you can catch me on that. The chlorite ion has got a T. Chloride ion, it's just a chlorine atom with a charge, and that's D. All right, where is it? Oh, there it is, ClO2. All right, ClO2. It's got a -1 charge. The copper, how about the charge on that? It's got a +2 charge. This is one of those things that's actually kind of helpful, where you're starting with that name, copper 2 chlorite, and it gives you the charge already. It's actually kind of easier. The mistake not to make is you don't want to call that, you don't want to say, oh, I guess the 2 is a subscript, because the subscript is not the Roman numeral. Here we have, all right, looks like we need 2 chlorites, because this is a +2 charge. I guess we need 2 of the chlorites to balance out the copper, the 2 plus from the copper. So, we're going to need to use brackets. The subscript here ends up on the chlorite, because this is what this is saying is in the formula there is 1 copper, 2 plus copper, and 2 of the chlorites, because your polyatomic ions, every different kind, has got its own charge. You don't have a nitrate with a plus of the -1 and one with a -2. No, you don't. Any given polyatomic ion has its own charge that it always has. So copper 2 chlorite is Cu, then brackets ClO2, the 2. Here, let me focus on that a bit better. Whoops. That's copper 2 chlorite. The next 2 I'm going to do, and then I'm done with examples. Manganese 2-phosphate and manganese 3-phosphate. All right. So again, they're actually giving you the charge, which is actually kind of useful. As long as you know how to interpret it. Manganese 2 means that the ion in question is manganese with 2 electrons stripped from it. It's a 2 plus charge. The manganese 3, the Roman numerals, it's got 3 electrons stripped from it. +3 charge. Now we need to find our polyatomic ions. Well, the phosphate ion, again, if you had an impossibly powerful microscope, you would find the phosphate ion it's a phosphorus with 4 oxygen atoms around it, and overall it's got a -3 charge. So it's a very negative ion, very reactive compound. Bad for waterways. All right, now we need to figure out where that's going to take us when we make our formula. Let's do manganese 3 phosphate first, because that one actually isn't too hard. It's not too hard because the manganese with the 3+ has got the same charge as the phosphate with the 3-. It's just the positive and the other is the negative, but they both have a value of 3. What I'm trying to say is the charges cancel each other out perfectly. So we don't need any subscripts. Manganese doesn't need a subscript, and the phosphate doesn't need a subscript. This stuff is MnPO4. 2 things I'd like you to notice. One is that there is a subscript there, but it's a subscript for the phosphate. Phosphates always have a phosphorus with 4 oxygen atoms around them and a -3 charge. Every phosphate in the universe has got that by definition. But you don't have that situation where there's a bracket around the phosphate and then a 3 underneath that. No, that's not there. And the manganese, it doesn't need a subscript either because the +3 and the -3 balance each other perfectly. How about the manganese 2 phosphate? Here, using the same rules that I've already taught you. Let's write out our formula, our formulas for our ions. Well, Mn2+ is manganese 2. So we've got phosphates with a -3 charge. I guess I could walk you through this, but I kind of feel like not doing that, other than just to say this, that the positive and negative charges have to balance each other out as well. Intuitively, you probably know that to make that happen, you're going to have a +6 from one and a -6 from the other. The lowest common multiple rule is being used here. The lowest common multiple of 3 and 2 is 6. So your positive charges have to be +6. Your negative charges have to be -6. And that way the charges can balance perfectly. The manganese 2+, that +6 is divided in it's divided 3 ways, because 6 divided by 2 is 3. We need 3 manganese ions there. As for the phosphates, each one of them has a -3 charge. We got a total of -6 negative charges to make, and that can be evenly divided between 2 phosphate ions. So what are our subscripts? 3 manganese, 2 phosphate. All right. I'm going to get the camera directly on that. That, in my opinion, is about as hard as any chemical name problem is going to get in Science 9. The subscript for the manganese was 3. The subscript for the phosphate was 2. Again, I'd like you to notice that I had to use brackets around the entire phosphate to get the number of phosphates involved, 2 to the 3 manganese. So that's the one thing I wanted you to notice. Oh yeah, there's one other thing I'd like you to notice. Again, don't confuse the formula for a polyatomic ion with some kind of element symbol from the periodic table. Another common mistake I might see is if someone sees, say, MnPO4. Again, a common mistake might be like, okay, well, I guess PO must be polonium. No, it's not. The element symbols have always got capital letters. So polonium, that deadly metal, is capital P, little o. The capital versus lowercase really matters here. Whereas phosphate is big P, big O, and then a little 4 at the bottom to tell you that there's 4 oxygen atoms in play there for that one ion. That's all the teaching content I wanted to show you today. I just thought I'd show you something really cool. You can turn this off now if you want, or stick around. This right here is iron 3 nitrate. How do I know? Each nitrate has a -1 charge. There's 3 of them. This means that there's a -3 charge to balance. This iron has got a positive 3 charge. So it's iron 3 nitrate. This stuff right here looks kind of uninteresting. It's ammonium thiocyanate. The thiocyanate ion, it's kind of cool. It sounds deadly. It's actually not deadly poisonous. Cyanide is really nasty stuff, but thiocyanate is where you take a sulfur atom and you connect it with a cyanide ion. So it's actually an ion that's a line. Sulfur, carbon, nitrogen. 1 bond between the sulfur and the carbon, and then 3 bonds between the carbon and the nitrogen. Hey, did you notice that the carbon has a total of 4 bonds? That's a general rule for carbon. You might remember that from my lesson about diamonds. Let's look to see what happens, though, when we take a clear solution of one thing and combine it with a clear solution of another. So let's get some, actually a rusty-colored solution of another. So let's get some of our thiocyanate. Some water here. All right. Oh, there it is. Be able to see that super well, but this is a thiocyanate ionic compound that is in water. The formula for this stuff is NH4SCN. This is an example of an ionic compound with polyatomic ions where there's no metals at all. Nitrogen, hydrogen, sulfur, and carbon. There's no metals, but the ammonium has a +1 charge. The thiocyanate ion has a -1 charge. So NH4 is the positive part, and SCN is the negative part. Most of the ionic compounds you're going to see in high school chemistry have got a metal and a non-metal. But chemistry is full of exceptions. I'm going to show you a test for the presence of the iron 3 ion, because iron can exist as iron 2 or iron 3. I've taken a little bit of this here, made this very pleasant amber-colored iron 3 solution, and I have this clear solution of ammonium thiocyanate. See what happens. I'll be honest, it's one of my favorite demonstrations in chemistry. It doesn't show up perfectly well. You know, I'm going to get a test tube to show this a little bit better. Here, watch this. Look at that color there. So these are very dilute solutions. There, that's starting to show up a little bit better. It's a very distinctive color, isn't it? Kind of a wine red color almost. But that's not what it's been used for. This stuff here, I've made a polyatomic ion that's actually really big. It's called an ion complex. In this ion complex, that iron 3 plus ion has bonded with the thiocyanate ions to make a really big ion that's got iron, sulfur, carbon, and nitrogen in it. I can't remember how many thiocyanates it bonds with. Maybe 2. I need to look that up. Point is this, that some of you are probably interested in drama, I'll bet. Got a great school here for it. And there's been a use for this in the past. That if an actor on stage wanted to simulate that they were being murdered, or someone, if that was part of the play, I guess, they would take a bag, a small bag, that was divided into 2 parts. One part thiocyanate solution, the other part an iron 3 solution. And the one character then takes a stage knife and they stab the person. I guess they're probably wearing a white shirt. And these very dilute solutions of iron 3 and thiocyanate join with each other and react, and it looks as if the victim of the murder is absolutely gushing blood all over the stage. Well, they weren't, but they are gushing the iron thiocyanate ion complex. So that's your drama for today. I hope that's interesting to you, and I'll be posting an assignment that has this as well once I've got it ready.